All right. So for our next speaker, we have Stefano Andriolo from Bangor University to tell us about self-binding in AdS and the weak gravity conjecture.
Yeah. Thank you, Monkey, and thank you, Eduardo, for inviting me here. And I hope you can see. So can you see the mouse actually? Because I cannot see the pointer myself. And
can you move
maybe
pointer?
I mean, I cannot.
Okay.
So maybe is it a problem if I keep it like this, or maybe I do it?
I think you have to press Command C when you're in presentation mode. When you're in presentation mode, Command C.
Yeah.
Yeah.
Oh, thank you very much. Yeah, perfect.
You're welcome.
I'm not that tech savvy. Thanks. So basically, yes. So this is like I'm going to talk about the weak gravity conjecture in AdS and how to formulate it using the concept of self-binding energy. And this is a work that appeared a few weeks ago on the archive in collaboration with Eran and Marco here at Bangor University. So my talk it concerns concerns the Swampland program, which aims at figuring out the criteria for which effective field theory can be completed into quantum gravity. And we know there are many different such conjectures. And I'm going to talk about the weak gravity conjecture as one of this. In this slide, I just want to point out, before moving to some motivation, I just want to point out some notation conventions. So in the former version of the electric weak gravity conjecture, in flat spacetime, in the dimension, the statement is the following. In any consistent U1 gauge theory coupled to gravity, there must exist at least a state satisfying this inequality. So, and what I want to point out is that I will consider this statement as a statement regarding particles with some order 1 charge. So in particular, I'm not concerned with black holes. And in case of multiple U1s that have been canonically normalized, this inequalities generalizes with this sum on the gauge forces on the left-hand side. And you can further generalize it, as shown in this paper by Ran, in presence of additional neutral massless Yukawa coupled scalars. And this will give a modification of the right-hand side. Basically, they will contribute as an additional attractive force like gravity. And this guy, as will be clear later, is the so-called Yukawa charge. It's directly related to the Yukawa coupling of these objects. So I can move to some motivation now. Modeling out some subtleties. Also, I don't want to spend too much time on this. So I want to start from probably the best understood Swampland criteria, which is the absence of exact global symmetries in quantum gravity. You can think about this like a global U1, for example. You can motivate this more and less rigorously. The more rigorous way to see this and to understand this is in perturbative string theory and in a DSFT. And a less rigorous way is using black hole heuristics. And for instance, you can think about the tension between the no-hair theorem and the finiteness of a black hole entropy. And the Gedanken experiment goes as follows. So you can imagine to have a black hole of some fixed mass, and if you want other gauge charge, angular momentum, but for simplicity, you can just think about a Schwarzschild black hole. And this can have any global charge. This is not reflected in the horizon. And what does it mean is that from external observers, there is an infinite uncertainty related to the Schwarzschild geometry. And so this is directly linked to an infinite entropy, which is in contradiction with the Bekenstein-Hawking finiteness of the entropy. You can also rephrase this consideration using, showing that a single particle with a global U1 charge give rise to an infinite number of stable remnants after Hawking evaporation. But I'm not concerned to this right now. What I want to point out in this talk is that you can rephrase this story in a bottom-up perspective. Let me put this here. In terms of, sorry, okay, in terms of an infinite number of stable bound states. And you can think about the following. So you can take two copies of the same particle with mass m and charge q. And if you have more particles, you take the one, so consider the one with the smallest mass to charge ratio, mass to charge ratio, where q is the global charge. So what happens? So there is gravity and only gravity in this system. So they will attract and they will form bound states. In particular, they will be completely stable because the mass to charge ratio of the bound state is smaller than the mass to charge ratio of the particle, of the initial particle. And this, since we are considering the one which is the smallest among the all other availables, this will be smaller than any other mass to charge ratio, which means that this guy cannot decay, this bound state cannot decay, because in order to be able for this guy to decay, you can show that basically one of the byproduct of the decay must have a smaller mass to charge ratio respect to this bound state here. So what happens, you soon realize that you end up with an infinite number of stable bound states, okay? So how can we ameliorate the situation? Well, we gauge the U1, and in this way we can get rid of this infinite number of bound states. And why is that? Because now gauging the U1 means that you are introducing an additional long range force. And now it becomes a battle between these two long-range forces, namely, the gauge, U1 and gravity. And who wins depends on the value of the coupling constant, the charge, and the mass. However, if you think about taking this limit, assume it's possible, let's assume it is, it's like, you see that's like restoring the global symmetry issue, because now this guy is basically suppressed with respect to gravity, so gravity wins, and you go towards that limit. So and here is the point where the weak gravity conjecture enters the reasoning, and it tells you that basically you better gauge the U1 strongly enough. And what does it mean strongly enough? I mean, this is a system where there are only gravity and gauge U1 forces, so probably strongly enough means that the gauge force has to beat gravity. So such that there must exist a particle for which gravity is weaker than the gauge force. So you get naturally this statement, and which was originally formulated as a super extremality condition regarding black holes, and in order to allow them to decay, basically, in order to avoid this infinite number of remnants, basically. And but as we just saw, this is equivalent. This is equivalent to this repulsive force conjecture that requires exactly the existence of a self-repulsive particle. And I will use this logic in this talk. This is what I'm concerned with. So you can, following this logic, you can think about, let me remind you, we are in flat space, not yet in AdS, okay? So you can think, you can ask yourself what happens when you add massless scalars. What happens is that you're adding another long-range force. Sorry, the mouse keeps disappearing, okay? And now the battle is a little bit more involved, and this additional long-range force mediated by the scalar, it's also attracting like gravity. So if you demand the existence of a particle which is self-repulsive among under all the forces, basically what you're asking is that the gauge U1 has to beat the gravity plus the scalar force, okay? So this mu here, as I promised, is basically encodes, as you can see, the Yukawa Yukawa coupling, which is 2m mu. In 4D, it takes this form. And this has good support from string theory example, in particular in this construction, F-theory commodification to 60. And you can see there are several, in the x-axis, actually there's the charge here. So these are all the bound state, all the non-BPS states that they find in this compactification. And you can see that they find the red and blue ones. So the red ones are the ones that are self-repulsive because they lay above this line. So laying above this line, which encodes the gravity plus the scalar force, means that the gauge force beats these two. And you find quite a few. So this conjecture seems to be well respected. But what happens in AdS? So we can follow this logic of demanding a self-repulsive particle and see what happens. The problem of AdS is that AdS is like a box, right? So it's not, we cannot separate two particles like in flat space-time as far as we want, in a way that only long-range forces are relevant. Now we cannot do this anymore, so we cannot really separate two particles arbitrarily far away, and thus this means that we cannot really neglect the short-range forces. So more accurate formulation for the weak gravity in AdS, taking this fact into account, has been proposed last year by Hofer and Era, and this is called the positive binding conjecture. And the statement is the following: for a weakly coupled gravitational theory with a U1 field, there should exist at least one charged particle with charge of order 1 that has a non-negative self-binding energy. So basically, this is self-repulsiveness, requiring at least one self-repulsive particle. But now the interesting point is how this self-binding energy is defined and how we can compute it, right? So it is defined as the difference between the energy of the two particle state with lowest energy and twice the energy of the single particle state, again with lowest energy. And using the Hamiltonian formalism, so this is the definition, and you can compute it using this matrix elements. And if gamma is positive, the two particles are basically the particles self-repulsive. They don't bind. If it's negative, instead they form a bound state. The particle is self-attractive. In case it's 0, and you have an interacting theory, you have a BPS state, which is this kind of floating object. Which doesn't feel any force. So what we want to do is to compute this gamma at 3 level, okay? And at 3 level means that it's going to be determined by quartic interaction of these two types. So either we have contact terms like this for phi, or we have field exchanges. And in particular, I will be concerned with exchanging photons, exchanging graviton, and exchanging additional scalar, neutral scalar fields. And this is the setup. So for such an effective field theory containing this type of interactions. And I just want to point out quickly, small m. So this is like the phi is the, as you can see, this is the covariant derivative. So this phi is charged under several canonically normalized U1s. This is its mass. And this is let's say potential. It's not really a potential, but for notational simplicity, let's call it potential, and then calls all the contact terms that you can write down. So all the quartic terms in phi, you can see, they will depend on some effective parameters, coefficients A, B, and C. And then there is the neutral scalar. A neutral scalar with mass big M, and it's going to be Yukawa coupled to the charge object, and also actually you have to consider also this irrelevant operators, because this gives precisely what is it? Yeah, trilinear vertex like this, and we will see that they will actually be rather important in the following. So how do we compute gamma? So this is in general really hard to do, but the situation simplifies assuming small interaction, because now you can treat this small interaction as a perturbation around the free theory for phi. So you can use standard perturbation theory in the Hamiltonian formalism to compute this gamma. And see, as I just said, so now the operator and the states are those of the free theory, which are really well known. So you quantize the free and the massive free system for a massive complex scalar. And the two particle states will be just of lowest energy are obtained acting with this creation operator at the lowest energy, which is, or all the quantum numbers set to 0 on the vacuum. So if you go from the action, you compute the Hamiltonian of the entire system will be like the free part for phi plus interactions. And here, small interaction. And here we can just focus on the quartic terms. And why is that? Because if you go back and plug, this Hamiltonian of the system back in here, you'll realize that only the quartic interaction in phi to the 4, let's say, are relevant. And so you obtain that you have to compute this matrix element, and this will be given by contact terms plus exchange. But the exchange, why this is just first order perturbation theory, you can easily do this computation. This requires this sum over all the intermediate states. That is really remarkable to perform. So, however, we have a shortcut. We are in luck, as shown in this paper by Fitzpatrick and Shi in 2011. We can classically integrate all the exchange fields. So in our case, all the photons, the graviton and the neutral scalar, to obtain a 3-level effective action completely in terms of phi. Okay, so you get the free piece like before, and now you have this effective potential that encodes all your interactions. So these are the contact terms that I wrote in the original setup, and these are all the other effective interaction that rise from this integration procedure. And what do they correspond to when you go to the Hamiltonian? They will correspond to other additional new contact terms. So they will be quartic terms. And in this way, this means that you can compute gamma within completely within first order perturbation theory, computing these matrix elements and performing this integration. So now I can be a little bit more explicit. So when you, so what does it mean to classically integrate out these objects? It means computing the equation of motion and plugging them back into the action. So you can see these are the equation of motion for the graviton, for each photon, and for the scalar chi. And these are the sources. The sources are all bilinears in phi, which means that also when you solve this equation of motion, all these objects, the graviton, the photon, and chi are going to be bilinear in phi as well, which means that all these objects that you can compute implicitly, they have this form, will be quadratic, will be quartic in phi, okay? This is bilinear, which means this thing is quartic, and the same thing for the photon exchange and then the scalar exchange. And however, the point is that even though this is really nice and general for any dimension, basically this is a really generic way to obtain this effective potential for any dimension really implicitly. When you want to do this actual computation, you have to really specify the dimension and go and solve these equations. So we did this in d = 4 and d = 5, and
Stefano,
I'm gonna show you
roughly 5 more minutes.
Okay, great. These are the results in d = 5, and I just want to point out that delta here encodes is a proxy for the mass of phi of your charged object, and for CFT reasonings for unitarity, it has to be bigger than 1. And you can easily see that. So this is the contact this is like the contribution to the self-binding given by the contact terms. So depending on A, B, and C, this is like given by the photon exchange, and this is the graviton. And we computed also for the scalar exchange for a massless one. It's rather complicated, nasty looking thing, but and also for the BF saturation for when a BF bond is saturated. And it's a little bit simpler. So what we can do with this? So we did the same in also 4D. And oh yeah, sorry, this is also a slide about the numerics for all the other like, because this is an analytical result and this is the numerics. We just wanted to check that basically our analytic results are really well interpolated by the numerics. And also there is a caveat on the validity of the perturbation theory, but I don't want to spend time on it. So now that we have we computed the self-binding energy, we have this nice formulas. What we can do is test our expression. So we did two tests. We took the flat space-time limit and we checked whether we can get the weak gravity conjecture in the flat space-time. And we checked that gamma is saturated by BPS states, as you would expect also. In flat space-time it holds. So so the flat limit, it's really interesting. So you have to take it properly. So this means that you have to keep in particular all your effective field theory parameter fixed. And in particular, so it means that you have to take not only the radius to infinity, the AdS radius to infinity, but also delta, for example, to infinity. So if you start with the positive binding conjecture that requires gamma to be non-negative, which is the sum of all this contribution, and you take the leading order in this limit for each terms. So the photon is this, the graviton is this, the scalar contribution is this, and the contact term is this. You can see immediately two things. So one is that, as expected in flat space-time, the contact terms are suppressed with 1 over L. And the second thing is that you find actually a correction to the standard. This will be the standard I showed you before, weak gravity conjecture in flat space. And you find a correction given by the irrelevant operator, which is, however, yeah, it's suppressed with M over M Planck, but nonetheless it's there. And the same works, exactly the same thing works in 4D, where there's a different factor here due to the dimension difference. The second test is we answered for BPS states, and we did this in n equal to d equal 5 and n equal to d equal 4. So in particular, now we took this supergravity from this paper, and we gauged the two U1s, so U1 cross U1s in the standard gauge supergravity formulation. We looked for AdS supersymmetric vacua, and we expanded the action around this vacua to obtain the effective action. And we obtain the effective action of the type we studied. I showed you in the setup. And we can work out basically all the effective parameters in terms of these so-called gauging parameters beta and gamma that enters this gauging covariant derivative. Yeah, and you can and then what we did is compute the binding energy for the charged object in this effective field theory, and these are the expression in terms of our beta, which is the gauging parameter, and delta. And if you sum this, this is 0. It's, yeah, you can trust me, it's not really easy to see from here, but maybe in d equal 4 it's a bit easier. It's the same thing. In this case, instead of gauging two U1s, we only have the graviphoton, so we only gauge this guy. And we did the same thing. We look for AdS supersymmetric vacuum, and we expand around it. And we find all the effective field theory and with the parameters. And you can immediately eyeball this when you compute the binding energy. The contact terms contribute like the scalar exchange with twice -3/8, which is -3/4, plus 5/4 is 1/2, which cancels precisely the gravitational exchange contribution, the contribution given by the gravitational exchange. So also in this case, the total binding energy vanishes. So let me wrap up. And sorry if I've been a little bit took too long, but so this is the summary and some future directions. So we motivated the positive binding energy proposals as a formulation of the weak gravity conjecture in AdS. and described a way to compute the self-binding energy in explicitly in D equal 4 and D equal 5. So that actually the way we describe it is quite implicit, as I told you, but we did it explicitly in D equal 4 and 5. And we checked in these cases that it survives two tests, namely the flat space-time limit. And it was interesting that we found an additional contribution to an additional correction to the original weight gravity conjecture in flat space-time. And also we checked that for BPS states, as expected, we have a vanishing self-binding. So what's next now? So we can do a lot of things actually. So you can either test no BPS states in string theory setups. We have been looking a bit into this. It's not really easy, however, to figure out this kind of effective field theory. But so the goal is to check that gamma is indeed positive for no BPS states. We can extend this to fermions and or more charged particles and check this formulation with the Tower statements and sublattice statements regarding the weak gravity conjectures. What happens, you can ask also with higher derivative correction or in AdS3, which is interesting because the standard model possesses a competition to AdS3. So if you can talk, if you figure out how to bind quantities in AdS3 after this competition, you find bounds on standard model quantities. However, the story is a bit complicated in the AdS3. And you can check also what you can do. This is something that I'm looking into it right now. It's work in progress. You can check the relationship of the positive binding conjecture against versus superradiance or other kind of instability in conditioning for black holes in AdS and super extremality. And then there is the whole CFT side of the story that I didn't even mention, and as pointed out in Rans and Hofer's paper last year. So it's pretty interesting, I think. And yeah, anyway, thank you very much for the patience. And yeah, if you have any question, yeah, you're welcome.
Let's thank Stefano for the very nice talk, and let's use clap emoji. Yeah, Lars, do you have a question?
Yeah, thanks for the nice talk. I sort of have two questions. So one of them is, so you evaluated this gamma in some particular state, like 2 particle versus 1 particle state or something like that. Maybe you mentioned it, but like what is the vacuum state that you select in AdS? So what I mean is you're considering like sort of a single particle state on top of some like vacuum state. And then I guess you have to choose a particular vacuum state, like Hartle-Hawking or something else. Or...
Yeah, well, I mean, this analysis is not really, it's not really dependent on that actually. It's more, okay, now I have to, well, in order to understand this, you have to handle a bit details, so, but I didn't write anything yeah. So basically, when you compute this object, let me see, it's here. Yeah, here, it's not really relevant because I mean, what you have to plug in here is this guy here, right? So what you are concerned with when you do that, and there is also a normalization factor here, by the way.
Yeah, I guess what I'm wondering is what is this zero, like the cat?
Yeah, but it's not really relevant because it annihilates, right? It gives you like an overall. You can just use commutation relations, and basically you end up with bracketing 0 with the vacuum, so it's basically 1. So I don't think it's particularly relevant to this. It looks like, in other words, I think you can pick any vacuum.
I see. Okay. And then maybe the second question is like, what is your definition of superradiance?
Oh yeah, cool.
Because it's a little bit tricky, I guess. Like you can sort of take multiple definitions. Or...
Yeah, I don't know. What is your definition of superradiance? So, I don't know. I think I don't know. I've been looking to the literature, and somehow not completely clear. What is clear to me is that apparently there are two different types of instabilities for asymptotically AdS black holes. One will be the superradiance, and the other will be the near horizon scalar condensation, they call it. And the superradiance here will be something that happens that affects mainly small black holes, small AdS horizon loss on black holes. And but yeah, I mean, the definition of which, probably you have a better understanding of it. I mean, I just started looking into this, and but do you have a clear? I mean, what's your definition of it, let's say?
Yeah, it depends a bit who you talk to. Like, you can derive like a condition based on like the first law of like whole mechanics. That's like if you scatter something, that it takes energy away. But some people would say it's not enough, and you really need to have like sort of a classical scalar instability that you form this.
No, I refer to that one. Yeah, I refer to the second one. Yeah. Sorry, it's not the first one. Yeah, then I'm referring to the second one. Yeah, that will be my definition.
Yeah, that's clear. Thanks.
Edu?
Yeah, thank you for the very nice talk, and also for the one in yesterday. I wanted to ask you. I wanted to ask you. If you could say a few more words. What is the problem exactly? The problem that you find in AdS3, and what self-binding energy? So what computation do you have in mind that could give phenomenological implications or some bound on some parameters of the standard model of whatever it is that you have thought about this?
Yeah, the thing is that I don't know if it's really doable actually, because in the AdS3, not only gravity is non-dynamical, but also the gauge. So here, when you go and try to solve, it basically means that you don't have equation of motion for where is it, for the graviton, for the gauge field, right? So it's a little bit complicated. I mean, I think you have to really think deeply if you want to pursue this story. I don't know, probably you have to redefine things. But the point is that if you manage to write down some inequality in AdS3, then since you are in the AdS3, you can think about commodifying the standard model. You know that you end up in AdS3. So if you manage to have an inequality of some that has some meaning in AdS3, so you can relate it to standard model quantities. Yeah, like you did in the previous paper with Luis and
that was
something like that. Yeah, regarding neutrinos. I don't think it will regard neutrinos. I think something else. But I mean, it's something that you can surely do.
Thank you.
All right. Let's thank our speakers today, and thanks a lot for coming in today. And then we're gonna rejoin in 2 weeks, which will be our last seminar in this year. See you later. Thank you so much.
Thank you, guys.
Thank you for attending.
See you.